Hello there. In this video, I'll be discussing logical signals, the secret mechanic behind how they actually work, and how we can use that information to shape more neurons. So let me start with by explaining what I mean by logical signals. This mostly revolves around how different neurons interpret signals. So for example, in this big category here, all of these neurons take what I call analog inputs. So what I mean by that is the value of the inputs matter in determining what these neurons do. So for example, for the UFO, if I send a small number, it's gonna move very slowly. If I send a large number, it's gonna move fast. If I send a negative number, it's gonna move backward. And like for the sliders, for example, it says how far they move, and so on and so forth for all of these different neurons. Now we make a distinction with these different neurons, which I consider having logical inputs. So what I mean by that is they only interpret their inputs as high or low, basically on or off. All of these neurons only have two states. They're either activated or not activated. And the common knowledge is to activate them, just send any number that is not zero. So if their input is zero, that means they're not activated, they're not going to do anything. But when you send a input that is not zero, no matter how big it is, like for example 1, -1, 0.1, it doesn't matter what value it is, as long as it's not zero, it's going to activate any of them all the same. Now, actually, there's something wrong with that statement. That's not entirely true. But it's still true that all these neurons only have two states of either being on or off. What's not true is that the only signal that doesn't activate them is zero. The truth is, this is the actual mechanics behind how logical inputs work. For all of these neurons, when they receive a number between negative 0.0001 and 0.0001, that's when they will interpret it as low or basically not activate them. And if a number in their input is either less than this value or greater than this value, that's the only time when it will be interpreted as high, or in other words, activate these neurons. Let me show you an example. Let's say we have a knot here, and we have a number object here. So we know that a knot, when it's not activated, when its input is 0, it will output a 1, and when it's activated, it will output a 0. And regardless of what input it gets, as long as it's not 0, it will output a 0. But here, from our new understanding, let's try 0.0001. So when I set this to 0.0001, you'll see that the knot actually outputs a 1 now. So even though there is a non-zero number inside its input, the knot still interprets it as low and doesn't activate. You can see here that if I move from this range to this range, so any number larger than 0.0001, so for example 0.00011, then it activates. You can see that the knot now outputs a 0. Then you might also notice that the connection lights up here. So that's actually the logic behind when the connections light up as well. So when the value inside the connection is between these numbers, that's when this connection will become thinner. And only when the value is larger than that will the connections become thicker like this. And see that again. Right now it's 0.00011 and it's thick. If I move it back to 0.0001, it becomes thin again and doesn't activate any logical inputs. Same for negative 0.0001, still doesn't activate. And if I make it larger, only then will it activate. So that's the secret behind logical signals in Game Builder Garage. Now we can take a look at these other neurons. So for these neurons technically accept analog inputs, but there is a special case of them. They will only activate when the value is within these ranges. So for example, for the game swap neuron, you know that when you send a value to a game swap neuron, it will activate swap to the next game, and then in that next game, output whatever signal that activated it. However, a swap game actually has a minimum threshold. Any value between negative 0.0001 and 0.0001 will actually not activate the swap nodon. Because of that, it's impossible to have a swap nodon which outputs any value between those two numbers. The same thing happens for the vibrate nodon, where it won't actually make your Joy-Cons vibrate if your value is smaller than that value. But if it's outside that range, it will still matter how big or how small that value is. It just it's just a threshold of when it will activate. And for this last category, it's just a mix of any of these three categories. So, for example, for the person, the movement, these two movements is analog inputs. The action is a digital input. And the jump input is pretty weird in such that it's technically an analog input, but it doesn't matter how big or how small the value is. So it will still activate when you send 0.001 to it, but it doesn't matter how big or how small the value is. It just for some reason accepts values smaller than 0.0001, unlike every other digital input here. And all of these other nodons have similar cases where they have a mix of the three. Now you might be thinking, well, this is certainly interesting, but how is this useful? Well, in this video, I'll just be running through all of the different examples where we can make use of this and exploit this fact to do things we couldn't do before and shave more nodons. So let's start with a simple example. So here I have a not nodon and a equals comparison nodon. So in some cases, you might think that these two nodons are identical. For example, if the input to both of them is 0, you know that the not outputs a 1 when the input is 0. And same for a equals comparison comparing to 0. So since there's a connection here, this comparison will only output 1 when its input is 0. And same for not, it will only output 1 when its input is 0. But when we look back here in our categories, you will notice that, well, the not nodon is here in the logical input side, and the comparison nodon is actually a analog input. So what does that mean? Recall that these rules only apply to nodons in this logical input category. So that means that for a not nodon, if we send a value of 0.0001, it will interpret that as low, or in other words, it will not activate it. You can see here, since the value here is inside this range, it does not activate the not nodon, and it will output a 1. However, for the equals comparison, the equals comparison takes an analog input, so it doesn't care how big the value is, but it still sees that, well, it's looking for 0, exactly 0, but the input is 0.0001. And because of that, it will still output a 0. So in this case, the not nodon and the equals comparison are different. So if in the past you've wondered, well, okay, I'm sending a signal that's not lighting up to an equals comparison, but for some reason it's not activating. That's because the number is within this range, so it doesn't light up. But technically that number is still not 0, so that doesn't activate the comparison. So in a way, the not actually kind of acts as some sort of detector for values within this range. If for some reason you wanted to know if a number is inside this range, you can use a not for it instead of using a bunch of comparisons. And this is actually a mechanic that we'll go much deeper into later. Another pair of nodons which is differentiated by this mechanic is the AND nodon and the division nodon. So sometimes in our code, for example, we have a analog value, let's say 0.1. But for some reason or another, we want the value to only be 0 or 1. We just want to know if it's high or low. So for example, we can connect these here to the AND. And we can know that if it's 0, we know that the AND will output 0. And if it's any number that's not 0, it's going to output 1. It's a very simple way of converting analog signals into digital signals of 0 or 1. Same thing applies to a division nodon. Since we're dividing the same number to itself, when the number is not 0, it just becomes 1. And if the number is 0, it becomes 0. But this distinction comes in again, where the AND nodon is a logical input nodon and the calculator nodon is a analog input nodon. What that means is, if the input is within this range, so let's say 0.00005, example, well, for the AND nodon, it interprets as both of these as logical 0 or low signals, so it doesn't activate. But for the division calculator, it doesn't really care about these rules. So it still takes the original number, 0.0005, divides it by itself, that's still 1. So we can see in this case that these two nodons behave differently, and which one you should use depends on what you want to do. For example, if you want to detect strictly for logical signals that you want to use for other logical nodons, the AND is probably better because it doesn't catch signals that normally wouldn't activate other logical nodons in the first place. However, if you're strictly trying to detect if a number is exactly 0, then a division nodon will be much better because it can still catch these cases that are really, really small and still say that, oh, that number is not 0. For this next example, I have a simple timer setup here. So this is just a setup where I have a counter that's counting up by a constant. And when the counter goes over 100, this comparison will activate and activate this texture. You can see here after 100 frames, this texture will get activated. Using the things that we know now, we can actually make this much more efficient. Let me copy this. And remember the logic behind logical inputs. Texture nodons are one of the nodons that take in logical inputs, so we can make use of it here. So remember, logical inputs only get activated when the value is greater than 0.0001. So like if a number is smaller than that, regardless of what value it is, it won't activate. And once it reaches that threshold, that's the only time when it will activate. So what if instead of sending a constant 1 here, we send it a value, a very small value that's smaller than 0.0001, and calculate it such that after 100 frames, the value inside that counter turns from a number smaller than 0.0001 into a number larger than 0.0001. So that after 100 frames, from this counter just counting on its own, it will be able to activate this texture. So let's try to do that. We know that a counter counts every 1 frame. So we want after 100 frames, the number inside the counter to become 0.0001. In that case, we just take 0.001, then divide that by 100. That will become 0.000001. So after this number is added 100 times, we will get a number that will hit the threshold of activating logical inputs. So let's try that. See that if we connect the constant to this counter, it will still look like 0, but see that after 100 frames, let me show that again. After 100 frames, both of these nodons activate at the same time. That's because at that moment, the counter's value went over 0.0001. But since the position of these display is like only up to 2 decimal digits, you don't actually see it. But believe you can see it from here. The signals in this counter is actually counting up, still counting up. The number is just too small for GBG to display it to us. So that's one neat way to make use of this knowledge of 0.0001 logic. So for this next example, I have a setup which detects when a number is between two numbers. So in this case, I have a setup which detects when the number in this counter is between 2 and 3. How it works is I have this comparison which detects when this number is less than or equal to 3. And I have this other comparison which detects when this number is greater than or equal to 2. So you can see here, when the counter is 1, it doesn't activate, only the stop comparison activated. But when it's 2, The bottom comparator activates as well, which activates the and activates the texture. Same for 3. And when we go to 4, a top comparison turns off. So this is a simple comparison setup. But you can see here that, well, we're using a bunch of different nodons here. It'll cost way too much. So is there a way for us to make this more efficient? So we know that there are actually two thresholds for activating logical inputs. It's 0.0001 and negative 0.0001. And we can actually make use of it by using maps. So let's take a map, set its output range to be 0.0001 and the negative output range to be negative 0.0001. Now what will happen now? Well, if the input is 0, it's going to become negative 0.0001. If it's 1, it's going to be 0.0001. And any number between that will be between those two numbers. And we know that any number that's between these two numbers will not activate logical inputs. And conversely, any number that's outside this range will activate logical inputs. So in this case, any number that's less than 0 or any number that's greater than 1 will be outside of this range and will be able to activate logical inputs. So let's say if I set this to 2 to 3, now see what happens. When the input is 0, well, we know that 0 is to the left of 2, which goes beyond this range. So it will result in a number that's bigger than 0.0001 and activate the texture. Same if I change the value to 1. But the moment that I set it to 2, it's going to be within this range. It's going to be negative 0.0001. You see here that when it goes to 2, we'll see that the texture, that the input going to the texture will turn off. And the same for 3. So when it's 3, it becomes 0.0001 because that's the other range here. And then the moment it goes over 3, it turns on again. And it doesn't matter regardless of what input we put here. Let's say 48, negative 48. So if it's like 0, doesn't activate because it's within negative 4 to 8. When we go below like negative 5, it activates. And if we go above, so we'll go to 8, go above 8, it becomes 9, it activates. So now, by using just one map and these settings, we can make a nodon that detects when a number is not inside a specific range. And it's really easy to set up. You just set the two numbers that you want to compare to in the top of this map. And now, right now, that's kind of the opposite of what we want here. So like right now, you see that if it's 0, this is turned off and this is turned on. And if it's 2, top is turned on, but this is turned off. So right now, this is inverted of what we want. So if we want to make a setup like this, which checks for when a number is in between two numbers, well, all we need to do is just add a not nodon here, and we will have the input that we want. So you can test it here. When it goes 2, it activates, and 3 is still activate, and then turns off. So conversely, for this other case, I have a case where I am trying to detect when a number is not inside the range. So from this previous example, we just added an extra not. So you can see here, when it's outside 2 and 3, this activates, and only when it's inside 2 or 3, that's when the texture is not activated. Well, in this case, we just use the same solution as before, but yeah, we don't need a not anymore. Or basically, we are adding an extra not here, but then two knots cancel out each other. So now we just have a one nodon solution of this one map set to 2 to 3 and like negative 0.0001 and 0.0001. And that can replicate this entire setup with just one map. So you can see here, if I move it to 2, that's when both outputs turn off. 3, 4 turns on again. You can just double check, like change the range to -1 to 5. 0 is inside -1 to 5, but when I move outside that range, -2, it activates. And then go above 6, it activates. So that's how you make a very efficient comparison between two numbers with just one node on. Now, one caveat with this solution is, if you look at the map, well, the range is just whatever range we set here in the top input range. But we know that the map is only limited to between -1000 to 1000. So if this is the solution that you're using, well, this is the maximum range that you can get. You can't use ranges outside -1000 to 1000 if you're using this type of solution. But that doesn't mean we still can't do it. Let's move on to this example. So in this example, I have a input that I'm comparing with this value. So this is just a map that generates 100,000, since we can't use constants to go over 1000. So this is just basically just a comparison that checks if A, input A, is greater than 100,000. So in our typical solutions with comparisons, like we can't use constants because constants only go to 1000, and same for maps, we can't do that. However, we can use the same concept of 0.0001 to somehow make a comparison that does this very efficiently. So remember, the number only needs to be greater than 0.0001 to activate logical inputs. Let's go down here. So what if we divide the input by a very, very big number? Let's say 1 billion. So if you watch the map shaping video, you would know that we can do that with just one map, division by 1 billion. So that we just set this to 1000, and I believe set 10 to, there we go. I think this divides the input by 1 billion. So let's take this input. So right now our input is 101,000. So if we divide 101,000 by 1 billion, we will get the output 0.000101. And notice that when you send it here, it's able to activate the texture because 0.000101 is greater than 0.0001. It's able to activate this. But when we set this to the input to 100,000, well, 100,000 divided by 1 billion is equal to 0.0001. And now the output of this map no longer is able to activate this texture. So by just doing a simple division on the amber, we were able to make a signal such that if the signal is large enough, the divided signal will still be able to activate the textures. But if it goes below a certain threshold, it will no longer be able to activate logical inputs. So by just using a map, we can actually do a comparison to a very large number. So any number larger than 1000 with just one map node on by just doing division. And the math to do that is just simple. Just take the number that you want to compare to. So in this example, the number that we want to compare to is 100,000. With that, we just take 100,000, divide that by 0.0001. That's basically the same as multiplying it by 10,000. So 100,000 times 10,000 is 1 billion. You just take 1 billion, let's divide the input by that value, and you will have a comparison to that original 100,000. So again, we're trying to compare with 100,000. So what we did was take 100,000, multiply that by 10,000, that's 1 billion, and just make a map that will divide by 1 billion. And then that map will just take any input it has, and if the input is greater than 100,000, it will activate logical inputs. If it's not, it will not activate logical inputs. So that's how you make very, very large comparisons, larger than 1000, with just one map node on. Now, one caveat of this is that remember that there's also still a second threshold for negative 0.0001. And unfortunately, this map node on will detect that as well. So let's say if I set this to a negative 100 and invert it, now this outputs negative 100,000. Negative 100,000 does activate either of them. Negative 101,000. Well, this only compares if it's greater than positive 100,000. So this still doesn't activate. But the map solution will activate for this case as well, since what it's actually detecting is whether or not the signal is greater than 100,000 or if it's less than negative 100,000. So be careful with that. In case you're trying to compare really, really large numbers, that can also be negative and you only want one or the other. Now let's move on to our next example. In this example, I just have two signals and I'm ending them together, activating this texture. So basically, when both of these signals are active, I want this texture to turn on. So in this case, we can also convert this to 0.001 line. You can also make use of 0.0001 logic to replace this AND node on. How do we do that? Remember, the rule is we just need to break the threshold to 0.0001. So one thing we can do is we can take the two inputs. So let's say we know the inputs are 0 or 0 to 1 or 0 to 1. We multiply the inputs by a number smaller than 0.0001. Let's multiply it by 0.00006. So right now, this button goes in this map. And when you press this button, this will send the value of 0.00006 to this texture. And since it's still less than 0.0001, it doesn't activate. Same thing over here. Connect this button to here. It gets multiplied by that 0.00006. And it's still not able to activate the texture. See here, when I press the buttons, nothing happens. However, when I press both buttons at the same time, well, these two signals individually are still less than 0.0006. But I guess to make it to illustrate it more clearly, when these two signals are added together, this signal becomes 0.00012 because 0.0006 plus 0.00006 becomes 0.00012. And now that value is larger than 0.0001. So that means when both of these signals are on, this texture will activate. And that's basically the same as this previous example. So by converting our signals to sub 0.0001 values, we're able to replace and node on functionality. Now, like looking at this, well, for cases like these, this is probably not worth it because you're basically spending more nodons to do the same thing here. So when would this be a viable solution? Well, what if the inputs are not buttons? For example, what if they're checking for certain conditions? Like say, checking if a certain number is greater than a known number. So for example, just replace it like this. Just imagine that just imagine these buttons are just some other variable that we're checking, and when we want to activate this texture, we only want it to activate when this number is larger than something, and this number is larger than something. So we need to use comparisons. So let's apply the same comparisons here to have them be the same. Now in this scenario, well here, we can't really do much since like we can't really shave these three nodes together. Like these are kind of unique to the function of this. However, when we look down here, well, if you recall from the map shaving video, we can actually convert comparisons into maps. And we can also combine comparisons With multiplication, we can do comparison and multiplication at the same time with just one map. So since we're already using maps here, so we can actually compress this comparison into the map by changing this map into a comparison map. Yeah, like that. Same for here. So now, when you compare these two, this case actually shaves one nodon. It was able to shave the n nodon. Because since we're already doing a comparison in the first place, the additional step of multiplying it by 0.00006 doesn't cost us any more nodons, and we're able to skip the and. So just to further illustrate the example, I've changed this setup to be like a case where we have these two inputs, B and C, and we're detecting if B is greater than 5 and if C is less than 5, and that's only the only time when the texture will activate. So we can convert these maps to do the same thing as these comparisons. So if we're comparing if something is greater than 5, we can just do something like this, or yeah, 5 point, something like that, and turn on range restriction. Then less than 5, we can do like this, turn on inversion and range restriction. So now you'll see that, well, right now C is less than 5, so this is active, and same thing for here. This map nodon is now outputting 0.00006. Then when B crosses the threshold of sort of 5, they still don't turn on, but when it crosses to 6, this comparison turns on, which activates this AND. Same thing happens here, where this map also turns on, makes 0.00006, and they add together, making 0.00012, activating this one. So when you compare these two scenarios, since the map is able to do the comparison and the conversion to just a very small number at the same time with one nodon, this setup now costs less nodon as compared to this setup. So that additional nodon is just for illustration to show you the signals lighting up, but yeah, you don't need it. You can just add the signals together here. So in this case, we're able to shave our AND nodons. Now, note that that doesn't mean that this is only useful if you can combine it with other comparisons and such. This also works if you're using the same signals again and again to do different ANDs. So for example here, in this case, each button is activating multiple ANDs at the same time. Well, when we convert it to our map setup here, so let me move them together. So each of these maps are the same as earlier. So this is just a map that converts 1 to 0.00006. Since each of these buttons only need one map to generate these signals, we can reuse that same signal for all of the ANDs that they're used for. So in this case, just by replacing these signals that go from 0 to 1 to 0.00006, since we know that each of them need two signals to activate each of these textures, we're able to do the same solution by using only 4 map nodons as opposed to using 6 AND nodons. So for a case like this where there's a lot of ANDs, maybe using this technique might prove useful for you. So this to show you here, when I go into the game and press different buttons, you'll see that yeah, the two systems work exactly the same as each other. But this side saves a few more nodons. So as I mentioned earlier, this concept of using the 0.0001 concept is useful for cases where you're checking for multiple conditions. And actually, even if you don't use ANDs, there are actually many cases where we check for multiple conditions. So one easy example is for these cases where we have like markers with bullseyes, or we have a square grid. So basically, like if you think about it, this marker and bullseye setup is basically just checking a bunch of conditions where, for example, this number 6 here checks for when the x input is like set to this value and when the y input is set to this value. And for 1 checks if both of these are 0. Like for this very last one, checks if both values are 3 and 3. So bullseyes are actually technically the same as a bunch of different ANDs, but it's just really, really compact and efficient and easy to understand. Now actually, It's possible to convert this into a sort of combinatorial setup where we can actually make use of the 0.0001 concept, actually shave a few nodons over this marker setup. Let me show you here. I already made a system here. So it might look quite daunting here, but yeah, if I show you the programming screen or in the game screen, you can see that these two solutions work exactly the same. However, in this solution, instead of using 16 bullseyes plus one marker and two extra map nodons, all I use are 12 map nodons. So these use the 16, yeah, 19 nodons. But by using just maps, we're able to shave it down to 12 nodons. So how did I achieve this? Well, I think it's much easier to understand when I move on to this uh, view. So here, so in this view, I just converted all of these textures to these number objects so that we can see how these map nodons work. Basically, what I did was, for this bottom counter, these maps basically just send a signal of 1 to all of the inputs in their specified column. For example, here at 0, it's sending 1 to all of these numbers in this column. If it's 1, it sends here, 2, it sends here, and 3, it sends it all here. And the same thing applies for this side. Here I do it the same thing, but for the columns instead, for the rows instead. So when I right now at 0, it's sending a 1 to all of the inputs at this row. It's 1, it moves on to here, 2, it moves on to here, and 3, it moves on to here. And if you'll notice, with this type of setup, there's gonna be one cell of all of them that's gonna have a value of 2, since that's the only input that's getting a 1 from both this vertical side and this horizontal side at the same time. Now, if instead of these maps sending 1 to these number objects, if instead they sent 0.00006, well, you can imagine that all of these ones would become 0.00006, so they won't activate any of the textures. But for this 2, well, it's going to be 2 of those signals, so it's going to become 0.00012. So now since it broke the threshold, it's going to be able to activate the texture. And so by doing something like this, by adding these signals, we can have something where only one of these things is activated at the same time that we can control using these two counters, which is essentially the same thing as this bullseye setup. And that's how we're able to use this concept to make a much more efficient setup than this bullseye marker setup. So to briefly explain how this setup works, so I have this counter. So this first map, it takes the input from the counter and has this kind of settings. 0 to 1, 0 to 1. Basically what this does is, if the input is 0, it's going to output 1 since this is set to inverted. So when it's 0, it's going to send a 1 to all of these, let me change this back. It's going to send a 1 to all of these numbers in the column. And it becomes 1, it turns off. Next, when it becomes 1, this nodon activates and sends a 1 to the second column. So that's why this turns off and this column turns on. When it goes to 3, or when it goes to 2, what happens next is, well, since this only checks if the number is 1 or greater, it's still outputting a 1. So to turn off this second column, we activate this map, which sends a -1 to this column when this number is 2 or greater. So what happens here is, in this column, we're adding 1 from the map here, then adding -1 to cancel it out, to turn off. And then we have this 1 extra map to turn on the next column. And the same thing happens for this last column. This map then, when this becomes 3, this map then disables or cancels out all of the ones here and sends 1 to all of this here. The same concept applies to the rows here. So These maps are exactly the same as these maps, so you can just see here, uh, they're exactly the same. You go up all the way here. That's how the setup is made. Then when we go down here, all of these maps are basically the same as all of these maps, except instead of using 1 or -1, we're using 0.00006 and -0.00006. Now actually, this setup is not the most efficient that you can get to, but in my opinion, it's relatively easy to understand. However, if you really need to shave those nodons, there is a more efficient setup that I've found. So here in our original setup, we're using 12 map nodons in total to control all of these 16 signals. In this setup, we're using only 7 map nodons, 1 extra constant, and 1 extra counter. So this counter goes from 0 to 4, 0 to 3. This counter is just half of that, 0 to 1. And if we check it here, we compare these two, the original to this one, it still works the same way. However, the connections and the values here is much more complicated and much harder to explain. So I won't actually go too deep into how this was made, just showcase you different things that you can do with this setup and give you the code if you just want to copy it for yourself. So to make it easier to understand, I've turned this number object setup to make it easier to understand so that you can see where all the connections are going and what the actual added numbers are when we scale them up to values of 1. So the first part is this bottom part, these constant and these 3 maps. So when I advance this counter, you can see that at 0, all of these are 1. It becomes -1, 1, -1. You might recognize this from the map shaping video, and this is just the simple way to activate logical inputs with just maps. But instead of just activating one at a time, we're activating the entire column. Now this thing is added with this other part. This is the vertical part, which does this thing. That goes from this part, -2's here and 2's here, and -2's here to 2's here, and they flip and they flip. And what results is this visualization where it's pretty similar to our setup before, but now instead of 2, we have a lone 3 here. Since the lone number is 3, instead of sending 0.00006, I'm sending 0.00004 instead, so that when 2 of them are added together, it'll be 0.0008, so it's still not enough to break the threshold, and only when there's 3 signals together, then the logical input will be able to activate, since it becomes 00012. Now the reason why this looks much more complex than the previous setup that I showed is because of how this value flips between 1 and -1. So I won't go too much into why, but that's the main reason, because to implement this shave, where instead of using 6 nodons in this row, using 3 instead, you have to use this flipping setup. And to make this work, we need to make a setup like this to have the same effect as before, where it flips between 3 and -3 instead of just staying at 2 at all the time. So now for this second setup, for the vertical setup, we can split it further into 2 more parts. So here we have a top counter and the bottom counter. So in this setup, the vertical part goes from 0 to 3 like before, but we have this extra thing that flips every other step to achieve the different state of the board for every value of this. So this one alternates every other value, and this one alternates every 2 values. So by combining these two, we get this result, which is our final result below. And if we look at the connections here, so for this one, for the bottom one, it goes from the original 0 to 4 loop, and we have 2 maps. So So the first map is just connected to the bottom two rows, and the top map is connected to the top two rows. And these just alternate between -1 and 1 when the value goes over 2 or becomes 2. So for example, here, when the value is 1, it's outputting +1 to these bottom two rows, and when the value becomes 2, it will then output -1. And the inverse is here. So this is just the same as this one, just not inverted for these top two rows. For this other setup, this is the one that alternates every other value. For this one, the bottom map is sent to this row and this row, so basically the first and third row. And this is set to these settings, so the same as the map here at the right. And this is also the same as the second map here, but now this is connected to the very top row and this second row. So now if you combine this setup, and this setup, you'll end up with this setup, which will have this sort of behavior. So now you might hear that unlike the very original setup, the 3 doesn't move from here to here. When I change this, it actually moves very weirdly. And like, while here it moves like upwards, on the other side it moves downwards. So actually the mapping is quite different from the original part. So what will actually happen is here I've labeled each of the numbers here to see how they actually activate in sequence. So now it moves like that. Move here. When it is 1, it moves like that. When it's 2, it moves like that. And when it's 3, it moves like that. So it's no longer ordered the same way as before. So if you want to order it the same way as before, you need to arrange all of these nodons in the correct order. So here I just did that. However, you can see here that all of the connections are much more difficult to understand. But the reason why I started with this setup, which resulted in the weird ordering, is because this is much easier to set up on your own. And after doing all of this, you just need to move all of the textures to the correct spots to make it the same as before. Because doing this from scratch is quite difficult because, yeah, the connections are not very intuitive where each one is supposed to go. So it's much better to start with that relatively simpler setup and just rearrange all of the inputs back to their original place. So that's just to give a taste of what you can do with this 0.0001 logic. There's probably a few more different things that you can do with this. You can be creative with it. And this is just to give you the tools to make use of it in your own game. Might be able to use this. And that's all for this video. Thanks for listening and see you in the next one.